Hello, everyone, and welcome to this, our 13th weekly Ask an Astronomer. I'm Sam, I'm a PhD student at the Institute of Astronomy in Cambridge, and I'm actually hosting this week. So if we have technical problems, it's my fault, it's not Stefan's fault. But it does mean that I kind of get to introduce Stefan as a guest. So, yeah, Stefan, do you want to kind of introduce yourself and tell us kind of what you're working on?
Yeah, I'm Stefan. I'm also at the Institute, as you probably know if have been in here before. Um, so now I get to talk about what I'm working on, actually. I'm doing cosmology in the kind of broad sense, which is studying how the universe evolved, how the universe began, how it's kind of what it's doing on the large scale. In particular, my field is kind of the dark ages and reionization. So that's the time between where you had the cosmic microwave background, like so a few 100,000 years after the Big Bang, and when the first stars were created. So that's kind of well, years ago we thought it was kind of boring, a boring part of the cosmological evolution because everything was neutral and there were like no big fireballs. But it's actually quite interesting what happens, and I'm trying to find out what exactly is going on and when did the first stars get created, etc.
Cool. So we've had a number of questions in already, which is good. Please get your questions in if you have any. So should we start? We've got a couple on quantum fluctuations. So this is a seems like a cosmologically appropriate question for you, Stefan.
Yeah, I think that's something I had to work with once in a while. Um, so maybe let me just kind of start at the beginning so that everybody, like, if you have any questions in the meantime, just like let me know in the comments. Um, so when you have some space of, well, just a bit of space, right? There can always be particles in there, and there can also be particles, like even if you have a vacuum, there could be particles being created out of nothing. The reason for this is in quantum physics, there's this thing called the Heisenberg uncertainty principle, and tells you that you cannot exactly know how much energy there is in some space. So in particular, if you look at only for a very small time, you can't be very certain about how much energy you have. This means you could kind of borrow a bit of energy from the universe if you give it back fast enough. So what you can do is you can borrow a bit of energy, make two particles, and then, well, there are two particles, and then a particle and an antiparticle, right? So that's what you do with energy. And then they can annihilate again, and the energy goes back, and it's basically goes away. I mean, this is kind of not the kind of mathematical explanation, but that's kind of a good way to imagine how fluctuations work. So this is what we call vacuum fluctuations. You don't only have these in vacuum, you also have them everywhere else, but it's less exciting everywhere else. Um, so this is kind of how particles and energy and stuff in general can be created from nothing in quantum physics, like on small scale. So if you're like looking at your table won't disappear, and because it's made of thousands of millions and much more than millions particles, and they won't kind of all disappear at the same point, and you won't notice if one or the other particle occasionally disappears. And what happened actually in the early universe, so shortly, well, actually kind of during the Big Bang, so during the big expansion of the universe at the kind of beginning, what we know, and there were also these quantum fluctuations. And the special thing is the universe was so incredibly, ridiculously fast expanding that these fluctuations, so kind of particle and antiparticle got created, but they didn't annihilate again because they were just expanded away from each other. So far, the kind of um, explanation in pictures. And that's actually how everything got made. So at the moment, we think that the universe kind of, well, was kind of uniform and boring, like when it was kind of, well, not created, but like when it began. And all the kind of fluctuations, so there are humans are here, humans are not here, like there's a planet here, there's a galaxy here, there's no galaxy next to it. All these fluctuations, what we call them, have their origin in the quantum fluctuations that happen during inflation. So that's actually really impressive. And it works out, like the math works out really well. So that's kind of one of the reasons actually why we believe in inflation, why we think that the universe expanded so rapidly in the beginning, because it just works out really well with what we observe.
So all these in this kind of schematic diagram we've got here, all these galaxies that we see kind of at the present day, they're all because of these quantum fluctuations.
Yeah, right. And also, so these fluctuations were really small, right? I mean, they were ridiculously small early on, but even at the time of the cosmic microwave background, so that's this kind of thing 375,000 years after the beginning that you see there. those fluctuations were on the level of less than 0.01%, or let's say around 0.01%, so really small. And in the last billions of years, all this matter kind of collapsed into under its own gravity into things like galaxies and stars and planets eventually. Yeah.
Cool. Good. So we've had a question, I think, from before on the Slido, bit of a change of topic, should we say, about the biggest asteroid ever found. So this one,
I think that's one for you.
I think so. A bit smaller scale. So the answer to this is it's Ceres, which is a dwarf planet, and I think I can go stronger and say it's more than just the biggest asteroid ever found. It is the biggest asteroid. If there was an asteroid bigger than Ceres, we would, certainly have found it by now. So asteroids come in a kind of wide range of sizes, and actually there's far more of the smaller ones and far fewer of the bigger ones, which kind of makes intuitive sense. So they go all the way from things that are kind of dust sized through grains of sand and pebbles, up towards the sort of things we standardly think of as asteroids in movies like Armageddon, right through to Ceres, which is it's got a diameter of 1,000 kilometers. So it's a few times smaller than the moon, but reasonably big. Yeah, so it's a kind of nice spherical body, and the reason it's a dwarf planet, it's like Pluto. So to be a planet, a few years ago, people they got together and decided that a planet, it needed to be spherical under its own gravity. It needed to orbit the sun, and the third one is that it needed to have cleared its orbit of other objects. So the kind of issue people were having is that lots of objects are spherical and orbit the sun, but it's where you draw the line between planets and not planets. And they decided that it had to have cleared its orbit. So where the Earth orbits, or the Earth and the Moon system, it's fairly empty space. There's not much other kind of space rock floating about. But for example, Pluto, which I guess is the famous example, well, Pluto certainly satisfies the first two criteria. If there's lots of other, not that much smaller than Pluto objects orbiting around in a similar area, and so it was decided that Pluto would no longer be a planet, and we came up with this new classification of dwarf planet. And Ceres is one of these. There's currently 5 dwarf planets. There's Pluto, Haumea, Makemake, or Make. I've never quite worked out how to say this one, and Eris, and they all orbit way out beyond Neptune in something we call the Kuiper Belt, which is a kind of collection of rocky bodies. And then Ceres orbits in the asteroid belt between Mars and Jupiter, and it's the only dwarf planet in the asteroid belt, and by far the biggest of the asteroids. So I guess it's kind of a dwarf planet, kind of a very big asteroid. To an extent, it's a question of semantics, really, on that one. But good question. Thanks.
Oh yeah, there are a lot of new questions on YouTube. So we
are.
got one question about exotic matter, and I think there are many kind of things that are called exotic matter. For example, dark matter, which is a thing that we know, well, we think we know that it exists. All the other types of exotic matter are usually kind of hypothetical things that we have actually no idea about if they would exist, and they probably don't exist. Like things like opening wormholes or something like that. It's very speculative. So there's kind of no evidence or no real facts about that we could tell here.
I think the interesting thing with these hypothetical matter is that the maths works out, so people can design the mathematics that creates these particles or creates wormholes, and it's kind of consistent with itself. But we don't know if the maths that they've done actually describes our own universe. So it's possible to come up with lots of beautiful mathematical theories that could describe a theoretical universe, but it's whether or not they describe our one that's interesting. And a lot of these hypothetical ideas, there's no real evidence for them at all. So at the moment, they're nice mathematical theories at most.
Yeah, we got
lots of questions.
Yeah, so there was one interesting one about galaxies. So there was a galaxy question about what is a galaxy wall and a galaxy supercluster. So actually, there's kind of this naming convention is a bit not that clearly defined. So like things can be superclusters, and there can be superclusters or superclusters. They're still called supercluster. So it's kind of not that completely obvious what it means what. But usually you would refer to kind of a galaxy cluster, or well, let's start with the galaxy. I mean, that's kind of what you probably know is like the Milky Way is a galaxy that we are in. So a galaxy is just kind of a collection of lots of stars, like billions of stars. I think 100 billion stars are there in the Milky Way. And then you can have many galaxies together. It's what you call a galaxy cluster. And then you can just go on. So you can have multiple clusters together that form a supercluster. And usually these things cluster, like they like to go together because they're heavy and they attract each other. And yeah, Sam, if you can later go to the slide of the cosmic web that we have, I think there's a few slides after or before this one.
This one?
Yeah, right. Yeah. So what happens is on the kind of large scale, so when you look at the kind of whole universe and you see all these objects attracting to each other, then you have kind of, let's say you have two big objects next to each other, then in between there, like if you have more objects, they will kind of line along a line between the two objects. And if you have this in 3D, you will get a wall between two objects. So that's what people usually call walls, like lines that connect two massive objects. So you can have walls that are really large, like these walls that you see there, they're enormously large. Like the line that you see on the picture is about 2 million light years. So that's way yeah, I don't know. I don't even have a comparison to like, well, what's the distance, but it's like huge. Anyway, yeah, so you can have these walls. So there's like, oh, I don't even know all the names of the walls, but I think we found a few things that are kind of like there's usually every big survey finds kind of a new wall. Like the biggest thing they see is like the Sloan Great Wall or the like other surveys, CFA Great Wall. Like that's just always the kind of biggest structures that you can see. Yeah.
Yeah, lots of questions coming in. One that took my eye, I think, was a question asking around what types of stars could extraterrestrial life possibly be found. So, I mean, extraterrestrial life is it's a bit of a buzzword, certainly in astronomy recently, ever since sort of we found planets around other around other stars, and I think it's a really human question to ask. You know, whether there's other life. It's not an easy question to answer actually. People still aren't sure about what types of stars. So, with regards to what planets could be habitable, the kind of most basic thing that people talk about is what's the so-called Goldilocks zone. So, all life on Earth relies on liquid water, and while that could just be a kind of a coincidence that it's everything on Earth relies on water. Water is a particularly unique substance. It's got a lot of chemical properties which make it really good for life. And obviously, liquid water only exists between 0 and 100 degrees Celsius. And so, if you imagine if the Earth was a lot closer to the sun, then it would be much hotter, and all the water would probably have been evaporated off. But if the Earth was much further away from the sun, it would be much colder, and we'd just have ice. And this kind of defines a narrow zone, which is called the Goldilocks zone. You know, it's not too hot, not too cold. It's just right, within which planets could exist and potentially have liquid water. And actually, Mars lies within this zone for the sun, and this is why, you know, we think we found evidence that there was liquid water on Mars sort of billions of years ago, but there isn't anymore. But beyond that, there's interesting things that go on with stars. So all stars are very active systems. They're hot, they're very magnetic, and they throw off things called like coronal flares and coronal mass ejections, where they sort of fling out hot material and charged particles into space. And the Earth has a magnetic field which protects us from these things. But depending on the types of planets, if they have weaker magnetic fields, if flares are stronger from different stars, then that could pose problems. So for a while, people have been interested in looking at dwarf stars, which are quite cool, quite small stars. And because they're cool, the Goldilocks zone or the habitable zone would be closer to those stars than the Earth is to the Sun. But now people are thinking that maybe these stars are more active than we might have thought, and if these stars kind of throw off big flares into space, then this could pose a real problem. Lots of strong ionizing radiation is not good for life. And so it could be that these aren't such good candidates. So I think the only honest answer to this question is sun-like stars, because it's the only system for which we have evidence that there is life. You know, we haven't found any life out there. There's various theories about types of stars, but it's really not sure, and we need to get better at understanding how stars work, as well as kind of characterizing how planets are around other stars.
We got one question kind of early that I really liked. It was about it was asking what is space-time, more or less. And I think that's kind of a good question to ask, because I often say, like myself, and I think many people just say space-time without probably explaining what they mean. At least I do that. And actually, there are kind of two things that often fall into the category of, oh yeah, it's space-time. There's the one thing that kind of space and time are, well, not separate things, but connected, and they can kind of mix around in certain scenarios. I'll give an example in a second. And the other thing is when you talk about how space-time is curved, and how it kind of, well, rather how space is curved, and how does this affect the path of light and things like that. And especially for the first part, I think it's a really, it can have really surprising implications. So say you think about two things that happen at the same time. So let's say, imagine a train, right? So there's a train with like a long train. It's going on the track quite fast, and at the end of the train, two things happen at the same time. I don't know, someone turns on a light bulb. If this train would be traveling like kind of fast, like let's say half the speed of light, and someone would be standing outside the train and kind of looking at the two windows and seeing when those light bulbs turn on, for the person outside, those light bulbs would turn on at different times. So they would not turn on at the same time, where they do inside. So that's kind of the idea that if your space is kind of moving, like your space is different, then how time relates changes as well. So then things that might be at the same time for one person might not be at the same time for another person. So that's actually like a kind of important thing when you try to, like, you know, ask questions about relativity, about like Einstein's theory of relativity. And yeah, that's why it's important to kind of think about space and time in a connected way. And there's like mathematical description for that that we have now, so that's fine. And that's we use kind of all the time when we do things that have, well, anything to do with relativity, really.
But I think in the kind of what is space-time as well, people sort of think about it as this physical, you know, the kind of, a good demonstration is often, imagine like a trampoline, and you put a mass in the middle, and you can see that the trampoline bends, and therefore things follow not straight paths. If you kind of fire a ball across the trampoline, it doesn't follow a straight path. And it's tempting to think about space-time as this physical membrane, but it's more sort of a useful system for talking about what happens in it. It's a bit like asking, like, what are the three dimensions of the kind of, we normally think of like forwards, backwards, right and left, and up and down, and like, what is this made of? It's not really made of anything. It's just a convenient kind of stage that we say actions happen on top of.
Yeah.
And I think in the kind of, so this is like relativity, and trying to marry this with quantum mechanics, which we talked about early on, is a really difficult and active problem that people are struggling with. And what this kind of nature of space-time, I think, crops up in a, I'm by no means an expert on this, but crops up in this, in like, is space-time a real thing, or is it just this convenient way of talking about what happens?
Yeah. We got another question for you, I think. We got a Pluto question. So why is Pluto not considered an asteroid? Aren't its companions on the same orbit in other case, or a bigger planet?
Okay, so in regards to an asteroid, in this, astronomy is kind of beset by naming conventions that maybe aren't the most useful conventions. They were kind of created when we started looking at the skies and discovering things, but you know, maybe they're not the most scientific or useful one. Usually asteroids are sort of in the kind of relatively in the solar system. So we have the main asteroid belt between Mars and Jupiter, and there's other objects kind of near to Jupiter which we kind of call asteroids, but anything kind of outside of Neptune in the sort of Kuiper belt that I mentioned earlier, we don't tend to call those asteroids. Generally, asteroids, kind of those between Mars and Jupiter, are predominantly rocky objects, whereas those kind of in the outer Kuiper belt tend to be icy. Maybe water ice, maybe methane ice, that kind of stuff. So it's kind of a composition thing. It's kind of where are they, and just a kind of semantic naming thing, really, that we don't consider Pluto an asteroid. In the case of failed planets, you can consider that all objects that orbit the sun are failed planets, if you like. I mean, in a sense, like planet growth and the way planets grow and objects combine together to form planets, that's still an active area of research. And yeah, most asteroids, if something had gone slightly differently, maybe they would have combined or ended up in the Earth or in Mars or in one of the other things. Yeah, but it's a natural consequence of the formation by kind of accretion. So most of planet formation, certainly when they get big, is just a case that, say you have two normal sized asteroids that come together at low speed, they might kind of coalesce under gravity, and lots of things come in, and you kind of grow a planet that way by accretion. You just keep adding mass, and that naturally is going to produce some very large objects like the planets, but there's going to be lots of leftover stuff that never got close enough to a planet to form a planet, or kind of stayed small. So yeah, we can think of them as failed planets, but in the same way you can almost think of planets as failed stars. If they'd got enough mass in them to get really big, then nuclear fusion would have started and they'd have formed stars. So yeah, kind of a size distribution is just a natural consequence of the way things form.
Yeah. Okay, we got a kind of also early on we got a question about Hawking radiation, so maybe I can explain this a bit, because it's also has been quite an active area of research, well, ever since it was discovered, honestly. But also recently people have been thinking about some consequences of it.
Yeah, so the question specifically is kind of, whether we know about an origin, does it have an origin that we know? And it's kind of the other way around with Hawking radiation. So we've never observed it. We've never seen Hawking radiation. We don't have kind of experimental or observational evidence for it. It's such a logical theory, the way it's presented, that everyone is pretty convinced it's true. So the thing with black holes is that, so in a black hole you've got something called the event horizon, which is, if you ever look at a kind of a picture of a black hole like this one, the event horizon is this kind of region here, and inside which the gravity is so strong that nothing can escape, not even light. So no light can get out of there. But outside of that region, then light can escape if it's going in the right direction. Obviously, if it's headed into the black hole, then it will fall into the black hole. And because of quantum effects, so Stefan mentioned earlier in the question about quantum fluctuations that we can borrow energy, essentially. It's a weird thing to get your head around, but we can steal energy, and the more energy we borrow, the kind of quicker we have to pay it back. It's a bit like a loan from a bank, really. But imagine that you could borrow energy and create a kind of particle and its antiparticle companion. As again Stefan said earlier, you've got an electron and a positron. And if they came back together, they'd annihilate, and you'd give the energy back, and all would be well. But near the black hole, gravity is so strong that you can imagine that they get separated quite quickly. So in these quantum fluctuations, you can imagine that one of the particles gets pulled very quickly into the black hole, but the other one just happens to be heading in the other direction, and it manages to head out and become free. So what's happened from the black hole's point of view is a couple of particles have just appeared. It's got one of them, it's captured one of them, but the other one's gone off to infinity. But what we see, say sitting here on Earth, if we could measure this, looking at the black hole, we just see one of the particles heading towards us out of the black hole. And because energy has got to be conserved, conservation of energy is up to the quantum mechanical, ignoring the quantum mechanical fluctuations, kind of on average, energy's got to be conserved. And if these electrons are heading out from the black hole, that energy's got to come from somewhere. And it comes from the mass energy of the black hole. So over time, as this radiation heads out, the black hole will lose mass. And so, no, we have no evidence for it, but the theoretical underpinning is so sound and the mathematics work so well that pretty much everyone is convinced that this effect does happen. It's just far too weak for us to be able to measure it. Like it's such a slow process that we could never measure it.
Yeah, that was an amazing explanation. Okay, we got one more question about kind of the Big Bang, and the question was, what was before the singularity? The short answer is we have no idea. The long answer is we have no idea, and here's why. So basically, I mean, our model of the universe currently is kind of okay. We kind of said, okay, something started here, and like our model doesn't contain anything about what was before. And the problem is why it can't contain kind of anything of what happened before the Big Bang is because everything kind of gets wiped out. So when we talked about quantum fluctuations quite a lot today, and basically whatever would have been before the Big Bang, it would probably have been wiped out by these quantum fluctuations because they just generate random noise, and this random noise is like kind of really big because the universe is so small. So whatever was before, there won't be any trace of it. So there will be kind of no way for us to find out what was before. And the way science works is kind of we only try to make models that we can actually test, right? So if I come up with a model, oh yeah, because if I come up with a model, yeah, that's a normal model, and before there were like pink fluffy unicorns. I mean that might be true, it's probably not. But there would be no way to test it, so there's kind of no point in me making such a model. And well, also more realistic models. There's not really that much point. So with a caveat, there are some models that actually could theoretically be, and they could be detectable. So there are things like, I think it's like cyclic universes where the universe collapses and expands again. And in certain ways, we could observe kind of signatures of that. So that would be possible. That's kind of an exception. But usually in our kind of the most prominent understanding, we have no idea what was before kind of the Big Bang.
A lot of astrophysicists kind of, even those who work on the very early universe, sort of they start their work just after the Big Bang. They kind of let the universe was created or began. We know because we're here. Let's just take that as read and work out what's happened since. We'll ignore the first tiny fraction of a second and just kind of work with the rest of it.
Yeah, like kind of my field of study is kind of like, oh yeah, the kind of a few like begins, let's say 500,000 years after the Big Bang. Other people start a few seconds after the Big Bang, or a few minutes after the Big Bang, or really much earlier, like fractions of a second, like 10 to the minus 30 seconds or something after the Big Bang. But you never get to kind of zero on the scale.
Yeah. So we've got a good question here about how a parsec is defined and why, as astronomers, we prefer using parsecs to light years. So, yeah, we're a funny bunch, astronomers. My favourite thing about astronomers is, so in general science, and certainly in physics, most people agree to use something called the SI system of units. SI stands for, I can't remember what it actually stands for.
I think it's System Internationale or something.
It's in French. It's in something like that. And it defines a set of base units. So that the meter is the unit of length, and the kilogram is the unit of mass, and the second is the unit of time. And we can have multiples of that. So I don't know, like the kilometer, 1,000 meters, etc. But they go with like meters and kilograms and seconds is the basic. In astronomy, it seems to me anyway that we decided we're looking at very big things a very long way away. So what we'll do is we'll change our units to make them smaller. So rather than kilograms, we deal with grams, and rather than meters, we look at centimeters with something called the CGS, the centimeter gram second system of units. And I've never really quite understood that. So it's natural that rather than quoting distances from here to the sun or here to our nearest galaxy in centimeters, we need some kind of bigger units to make these numbers more manageable. So the parsec is defined based on an angle. So this is quite difficult to explain without a whiteboard, but I'll go for it. So I'm gonna move back from the camera a bit here, and I'm gonna imagine that Stefan above me is a distant star. So he's a very long way away, and then the very top of the screen above Stefan there's a background of stars which I'm going to assume that don't move. So Stefan, if you stay still, if I'm over here looking up at you, then you're kind of, if you can put your arm up to the top right of the screen, other way. Yep, so I'm going to see him projected against any background stars that are up there. But if I'm over here, I'm going to see him projected against background stars that are in his other hand, the one that's holding the pen. So against his ceiling, he is moving as I do this, and this is called parallax. And if you kind of don't want to test it, just find an object that's near to you, and you can close one eye and then close the other eye, and you can see that that object moves relative to something in the background. So what happens is that the Earth, it was kind of, I'm sure you know, the Earth goes around the Sun, and what this does is it creates a slight difference in our position over the course of a year. So every 6 months we switch from being on this side of the Sun to being on this side of the Sun, and this creates the same effect as me moving my head. But Stefan, or the nearest star, is a lot further away than Stefan, so this effect is very, very, very small. And then we can measure these movements of nearby objects relative to a background in something called arc seconds. So an arc second is 3,600 times smaller than a degree. So you can think about your protractor's degree is very small, and this is 3,600 times smaller. It's really difficult to measure, but we have certainly Gaia, the latest telescope, and a few generations before that, we're able to measure these movements really, really precisely. And if this motion is 1 arc second, so 1/3,600th of a degree, then we say that the distance to that object is a parsec. So par for parallax, sec from arc second, parsec. And objects which are further away have a kind of smaller apparent motion against the background, and objects that are nearer have a bigger one. Again, you can test this by looking at objects in wherever you are. So it defines a nice observational unit for us to do, and a lot of astronomy and the units we used is based on observations, because astronomy really started out as an observational science, and the first astronomers mapped the stars because they were used for navigation, certainly for early sailors on oceans and stuff like that. When you couldn't see land, they used the stars. So that's what a lot of early astronomy was for, and we kind of just stuck with the parsec rather than the light year. So a parsec is about 3 times longer than a light year. They're kind of similar in size, reasonably up to a factor of 3, and we just stick with the parsec rather than the light year. Although light years are a lot kind of easier to explain to people. It's the distance light goes in a year. That's a lot shorter explanation than me having to do this and get Stefan to hold his arms up. But like most things in astronomy, yeah, it's because of old observational reasons that we use the parsec.
Wow.
Cool.
That was an amazing explanation.
So we've got a question on string theory, asking kind of what is string theory? Are you a string theory?
Not at all an expert on string theory. I mean, not an expert on many things, but not at all on string theory.
My favorite thing about string theory is you can buy a book called String Theory for Dummies. Like, you get all these guides for dummies, but it says on like the first page that before you read this book, you have to have read Quantum Field Theory for Dummies. So it's not for proper dummy, educated, you know. But yeah, can you give a layman's
Yeah, right. I will try. So let me introduce a bit like kind of the current particle physics model, right? So at the moment we think everything is made out of well, basically a bunch of elementary particles. I think I even have a slide on this later in the part. And yeah, there we go. So let's start by atoms, right? So everything's made of atoms. Like every object that I have here consists of, yes, like one of the atoms of the periodic system, and every atom consists of protons, neutrons, and electrons. Protons are positive, neutrons are neutral, and electrons are negative. And these protons and neutrons consist themselves of quarks, and the quarks are kind of even smaller particles than those atoms. So we have 6 quarks, the ones that you see there: up, down, charm, strange, top, and bottom. And we are very creative with names. And up and down quarks make up the protons and neutrons. So you take 2 up and 1 down, or 1 up and 2 down, and to get a proton or a neutron. And the electron actually is its own elementary particle, so we don't think it's made up of anything at the moment. So that's kind of how we compose everything. Like all the other particles you need for more exotic things that you can produce, for example, in particle accelerators like the Large Hadron Collider, or other kind of experiments, or maybe cosmic rays. They do produce strange, like various particles, in particular muons, which is also kind of one of the particles that we have on the list. And now the idea of string theory, or kind of the idea that we had in physics a long time, was, oh, maybe you can unify this into a set of simpler things. So what we did before was we had things like, oh, we have electromagnetic electro things, and we have magnetic things. And then Maxwell came along and said, oh, this looks like the same force. I can just write down a few simple equations and then explain everything. And then people later came and said, oh, there's this weak force that does like decay, and there's a strong force that does that holds atomic nuclei together. And there's this electromagnetic force from Maxwell. And we can combine them all into this, what we call the standard model of physics. And of course, the kind of logical idea would be, oh, maybe there's an even simpler model where we can combine like all these, many particles, 16, 17, yeah, particles into kind of simpler things. And the idea behind string theory is, okay, everything is kind of mathematically, you can describe it as a certain kind of, like you can imagine it like a string. It's not really like physical string, but it behaves mathematically like a thing that can oscillate. So when you have a piece of string, you can oscillate it, and then you can have this kind of oscillation where the oscillation goes between your fingers, like you can have like kind of one big oscillation in between, or you can have different modes. So if you move your fingers fast enough, you can have kind of an oscillation of a string between them that has like a knot in the middle. So it has like two oscillations, or two pieces where it oscillates a lot. And you can go further and further on this. So right, you can get multiple different modes. And this is kind of the idea behind string theory. So you say every object is kind of this mathematical string, and these strings can oscillate in certain ways, and they can can be excited in certain ways, and then they behave like the particle they represent. So depending on how your string oscillates, it's a different particle, and that way they try to explain the particle physics model. It doesn't work out as neatly as all the other things before. So among others, need a couple of more dimensions. I think usually 11, but sometimes more or less.
At least 11. At least 11.
And you get like lots of weird mathematics, so it's not kind of accepted, I would say, but it's kind of an active area of research and kind of trying to find out where does it all come from.
It's sort of the best attempt people have come up with so far. Certainly, kind of the most thoroughly investigated.
Yeah, that's true. Yeah.
There's a similar while we're on this slide, asking about strange matter.
Oh, strange matter. So I'm not sure if you're talking about the strange that's on here. So let's just go with that one. So this strange on here is the so-called strange quark. So I mentioned before, up and down are the ones that we usually have. So what is it? 2 up, 1 down for a proton, 1 up, 2 down for a neutron. And what you can add is you can add a strange quark instead of the down quark, for example. You can have 2 up and 1 strange, and then you get a different particle. It might be called Hyperion, but I'm not sure. I'm not an expert. Well, I learned this once, but I forgot the names by now. But you can essentially combine all those particles. The special thing about the up and down is they are the lightest ones. So it's easiest to create those particles. And when you have the heavy ones, they could decay into the lighter ones. So it's kind of hard to build particles that are stable out of the heavy, like the top and the bottom, they're kind of very heavy. And charm and strange are also quite heavy particles. But yeah, they're like, I think there's a whole class of particles that include the strange quark that are commonly produced in like particle colliders. So charm and strange are explored for like a long time. Like even before we had the Large Hadron Collider at CERN, we could produce those and like measure exactly how they behave and what kind of particles you can form and what are the energy levels of those particles. So that's kind of all well understood. I mean, there's also another meaning of kind of strange matter where you could talk about dark matter, which is, well, usually it's called dark matter, but I mean, you could call it kind of different ways. Dark matter is the matter that we think is most of the universe made out of. So actually, I think there's 4 or 5 times more dark matter than normal visible matter in the universe, which we need to kind of explain how the galaxies behave, how the universe behaves as a whole, and like to explain rubbish explanations. And this kind of hypothetical dark matter was a really good fit, and by now, basically all the scientists believe that dark matter does exist. Well, there's some debates about, I mean, we don't know what it is exactly, we just know it's kind of something that doesn't interact a lot, so it's kind of, it's matter, it's there, it's gravitationally attractive, but it doesn't do much else. I mean, there's like a huge amount of dark matter going through your body all the time, and like passing through Earth, and it basically doesn't do anything. We didn't see dark matter do anything yet, except be there and act gravitationally. Which is a mystery that we're trying to solve. And there are lots of theories what dark matter could be, but none of them turned out to be true yet, or we didn't kind of find evidence for any of those yet.
Okay, so there's a question on black holes which immediately grabs my interest. So asking, can we use a black hole's energy if it's spinning? And the answer is yes, depending on what you mean by use. If we can kind of, if you want to harness it as an energy source, that's technologically, I'm going to go with difficult. I'm not an engineer, but I think they'd say that was difficult. But theoretically, yes. So if black holes are spinning, then they've got more energy than if they weren't spinning. So, you know, it takes energy to cause things to spin. But what black holes do when they spin is they do something called frame dragging. So this is kind of going back to space-time. And because black hole gravity is so strong, as they are kind of spinning like this, they pull along the space-time that's just outside it. So let's go back to a black hole picture here. So if you imagine that this black hole was kind of spinning, then it would be pulling the material that's just right next to it along with it. And so if we imagine that a particle went very close to the black hole but didn't go in, then it might be pulled along in the direction of the black hole and be given extra energy from the black hole. And if this particle then escapes from the black hole and goes out to a distant observer, say us, then we'll observe that this particle has more energy than when it went in with. And so that energy has got to have come from somewhere, and that the only place that can have come from is the rotational energy of the black hole. So yes, we can extract it, and if this carried on happening kind of indefinitely, then any spinning black holes would end up being non-spinning. But there's kind of a counter to that, which is the way black holes grow and gain mass is through accretion disks. So I think I mentioned this last time I was on, but black holes kind of grow or eat, if you will, through an accretion disk. So material comes in and it's got some kind of spin around the black hole. It doesn't fall straight onto the black hole, except in very rare occasions. And it forms a disk around the black hole. You can kind of picture it like a frisbee with a kind of hole in the middle where the black hole is. And because this material is kind of spinning itself, it's got angular momentum, the kind of technical word for it. When this material falls onto the black hole, it will give the black hole some of this extra kind of spin. And so actually, if black holes kind of grow in the normal way, then quite quickly they'll actually start to spin up. So there's kind of this balance of these two effects that could be going on that work out how much spin real black holes have. But theoretically, yes, you can get energy out of a spinning black hole. I'll leave that one up to the engineers to work out how to do it in real life.
Yeah, I suppose we have to get close to one black hole first, and I think that's already that is a long way away.
Yeah, I'm not volunteering to be on that space flight.
Okay, we got a follow-up question, I think, to my previous discussion about the strange quarks. So I think the question was, what does happen if one of those hits Earth? And I should say one thing that I omitted last when I discussed this. Quarks cannot be alone. So quarks are only present in kind of triplets, so in like groups of three. So for example, to make up a proton, you have 2 up and 1 down quark. And the reason for this is the following. So you can imagine, so quarks have a certain kind of charge. So it's not like electrical charge where you have plus and minus, but it's what we call colored charge. You can have 3 values. So just for kind of convenience, for like humans understanding, I think we give them like colors, just say, okay, let's say red, green, and blue, right? Just because we know those colors. And if you add them up, they get you white, right? So you say a particle has to be kind of color neutral or white from the outside. So inside the particles have to be, one has to be red, one has to be blue, one has to be green. They can also be anti-colors, like anti-red, but let's discuss this later. Yeah, actually, I mean, those 17 particles that you see there, they're actually a bunch more because you can have antiparticles of most of them. But yeah, back to the strange quark. So you cannot have a strange quark alone, so you have like a pair of three quarks. And what happens when you would try to pull one of those out, there would be so much energy that you would require to pull them out, that from this energy, you could just create another pair, quark-antiquark pair, and the pair you would just created, one of them would go back in the kind of to the other two, and the other one would annihilate with the one that you are trying to pull out. So we can't pull out a quark out of a proton or a neutron or any other particle. But of course, you can have some particle that includes a strange that's flying towards Earth. I mean, one thing is it would probably decay. So I think most of the particles made up, if not all of the ones that are not made up of like strange or charm or top or bottom, decay over time, and some of them have a longer and a shorter half-life time. So what would happen is they would fly towards Earth and either decay kind of on the way, or if they're kind of created in the atmosphere or created kind of shortly before they hit the ground, they might just hit the ground and then interact with some of the, like whatever atom they find, and then decay into normal particles. So usually you would expect, oh, it hits something, then there is a kind of weak interaction, so it's kind of like a radioactive decay, and it becomes normal particles, like maybe some alpha particles, maybe a bit of radioactive radiation, but really, really small amounts, just to say this. Like, if there's one atom, like kind of one, well, not even an atom, but one particle with a strange quark falling in, there would be one photon, or, well, let's say a few photons maybe of radiation coming out. So nothing you could like reasonably like notice in any kind of everyday sense. So all the kind of a big radiation from space hitting us all the time, it's basically not noticeable without like really good measurement instruments. Yeah, right. So maybe I should mention this anti-quark thing because I said it 3 times now. So yeah, there's an up quark, there's an anti-up quark, there's a down quark, there's an anti-down quark, there's an antiparticle for every quark, and there's an antiparticle for every lepton. So those are the green things: electrons, muons, and taus. There's no antiparticles for the ones on the right, so no anti-bosons. So just for the left particles, and they can have anti-colors. So let's say you have an up quark and an anti-down quark, let's say, and they would have the color. Let's say the up quark is red and the down quark is anti-red. Then you could put them together in a particle because the color equals out. It's kind of white from the outside, and those particles we call mesons. So those are particles that consist of 2 quarks. And they exist, like we can create them in particle colliders, and we can do nice experiments with them. And yeah. But stuff can hit the Earth, but it doesn't do anything particular. So not dangerous in case anyone's worrying. Okay.
Yeah. So there's a follow-up to the when I talked about accretion disks in black holes and why matter doesn't fall directly onto black holes. So the reason is, if you imagine matter coming from a really long way away from a black hole, it's really far away, and it has some small velocity relative to the black hole. If that velocity was pointing straight towards the black hole, then under gravity it will just fall in onto the black hole in a straight line, and that'll be fine. And if we imagine it has a small velocity upwards, like this, then while gravity is pulling it this way, it's going to move slightly upwards, and it's just going to miss the black hole, if you imagine. And so what it's going to do is it's going to end up orbiting the black hole. And so there's only a really, really narrow range of kind of directions of this particle's, or this material's motion, which would cause it to fall straight onto the black hole. All the others will cause it to just miss, and it will end up orbiting the black hole in exactly the same way that the moon orbits the Earth and the Earth orbits the sun. So ordinarily, if there was just this one piece of matter, it would carry on orbiting pretty much forever. Nothing really to stop it orbiting. The moon has carried on orbiting the Earth for billions of years. But what could happen is, if there's a lot of material which has all come in on different orbits, then at some point these might collide with each other. And when these objects collide with each other, you get something called kind of shock heating. So they're going to crash together, and the motion is going to be faster than sound could travel through the material. And if you think about sound as kind of going through the material as kind of like the warning of what's coming. So if you kind of imagine, say, a metal bar, you hit one end, and the knowledge that I've hit one end travels through the bar at the speed of sound. But if you imagine two big clouds of gas that hit each other, then yes, it would carry out a warning at the speed of sound. But if they've collided faster than the speed of sound, then it's going the collision is going to happen before either cloud knows what's happening. It's exactly kind of analogous to the kind of sonic booms you get from supersonic aircraft. So when they go through the sound barrier, when the aircraft is traveling faster than sound, the air that the aircraft is colliding with has no idea that the aircraft is coming. And in these kind of astrophysical situations, this can give out a lot of energy and make the gas very, very hot. And this extracts a lot of energy from the gas. And what happens when we extract energy from the gas is that its orbit shrinks down to smaller radii, and it circularizes. And there's kind of mathematical reasons for this, but really it's because circular orbits have the smallest amount of energy given the amount of spin that they have. So the spin is a lot harder to get rid of than the energy, so it kind of falls down into circular orbits. And when we've got lots of things on circular orbits, you can kind of think of them as a disk. These collisions will also act to kind of align all of the orbits into the same plane. And so relatively quickly, actually, from a random collection of matter in random orbits, you end up with, provided there's enough matter, you end up with this flat accretion disk where everything's in circular orbits. And from then on, it's just down to kind of viscosity, which we think originates from magnetic fields, so magnetic fields pulling on different parts of the disk, which causes material to fall inwards to the black hole. So this is why pretty much all matter that black holes get comes through from disks. Yeah. Okay, we've got a couple of questions on M87, which I think is also kind of black hole related. One of which I can answer, one of which I'm not so sure about. So I'll take the second one first because I know the answer to this one. So it's asking. So M87, for anyone who doesn't know, is a giant elliptical galaxy, and actually, it's the giant elliptical galaxy that this comes from. So we think that all galaxies have what we call supermassive black holes in the middle of them, which are kind of 1 million to 1 billion times bigger than the sun. And when these accrete, as I've just explained, they give out a lot of energy. And a lot of these objects can actually form jets of very energetic material heading outwards from the accretion disk, kind of above and below. So if we look at this kind of artist's impression, we've got the disk in the orange, and then coming kind of out the top of the screen is sort of the base of what could be a jet. Really high energy material traveling outwards at sort of getting on towards the speed of light, so a non-negligible fraction of the speed of light, relativistic speeds. And the exact way these jets are formed, it's still a bit unclear. We kind of have fairly good theories that work fairly well, but don't get all the intricacies correct. So the question asks, why doesn't the jet in M87 have a twin? So we only see one jet from M87, or one very bright jet from M87. And you're correct in your kind of question about whether it's redshift. So what happens here is we have something kind of called Doppler boosting. So if you imagine material traveling towards you and it's emitting radiation, then say I'm going towards Stefan, so we're going up the screen. So I've got my material here and it emits some light, but if you imagine, so light is a wave, so it might kind of, one point in its emission might be here, but the next time it emits it might have gone up to here, and so it's moved. And so what happens is, as the light is traveling up at the speed of light, because the object that's emitting it is getting closer to Stefan, Stefan will observe it at a higher frequency than it's being emitted at. So what happens is, if you imagine a wave like this with kind of peaks and troughs, is it all just gets squashed together because each kind of peak is emitted closer to Stefan. So he measures it at higher frequencies and therefore higher energies. For the jet on the other side of the disk, in which the material is kind of heading away from Stefan, the opposite thing happens. So the wavelength actually gets longer because each time it emits, the material's got further away from Stefan as it's heading away. And when the material is going at relativistic speeds, this Doppler boosting can have a really sizable effect on the observational properties. So yeah, one of the jets heading towards us will boost the radiation to higher energies and make it more observable, therefore, and the one heading away to lower energies, which would explain why it's harder to see. The other question is about synchrotron radiation from M87 in visible light. I don't know of this observation. I'm not going to lie. But if this is true, then blue shifting the radio waves that the synchrotron would be, I think, is probably the explanation that I'd have to go with on that one.
I think it would be quite a lot of blue shifting, right? Like
yeah,
would be unexpected at least. Like I mean, especially like I mean, it's easy to get redshift in a black hole or close to a black hole, because if you emit radiation close to a black hole, it has to kind of get away from the black hole, and this costs a lot of energy, which makes it kind of less energetic, or as we say, redshifts. But for it to be blue shifted, like to get more energy, you need an effect like you just mentioned, like this boosting or something, that could like increase the energy, but I'm not sure if it's enough to kind of turn synchrotron radiation into visible light. But I think that's something we can look up later and then discuss next time.
Yeah, we'll get back to you on that one. Tune in next week.
Okay, we got one. Oh. Yeah, we got a question about the rotational axis. Did you get this one?
Yeah. So it's asking, can the rotational axis of tidally locked satellites precess? So tidal locking is, I think the best example here is the moon and the Earth, because we're all kind of familiar with that. So the moon orbits the Earth roughly kind of every month, every 28 days, and the moon also rotates on its own axis roughly every 28 days. So what this means is that kind of the Earth is here and this is the moon, and so you can imagine kind of as the moon rotates and orbits, it always keeps the same face pointing towards the Earth. Like so, the inside of my palm is, say, the face pointing towards the Earth, which is why we kind of talk about the dark side of the moon, which is the face we can't see. So the dark side of the moon expression it's a bit silly because it's completely incorrect. So it's the face that we can't see, but if the moon is between us and the sun, then the face we can't see, the so-called dark side of the moon, is completely illuminated by the sun. So it's no darker than the side we can see. It's just we can't see it. But it's not. So the Moon-Earth system isn't perfectly tidally locked. So the moon kind of wobbles as it goes around. So it's not completely. It doesn't completely show the same face to us all the time. And actually, if you kind of Google a time lapse of the moon, you can see this happening. There'll be videos on YouTube somewhere if you check it out after we're done, and you can see that the bits that we can see of the moon change ever so slightly as it kind of does. I'm trying to demonstrate with my hands, it's not particularly clear, but it kind of does this kind of wobble as it goes round the Earth, because its rotation and its orbital period, they're not quite exactly matched up. And so overall we end up seeing something like 59, I think, % of the moon overall. So only 40% of it we never see, rather than 50%, because different bits come and go at different times. So I'm not sure if this answers your question, kind of on precession, as to whether, I guess you're asking whether over time, like it would be a different face that would be presented to the Earth. So you could imagine, say, if the moon's rotation period was slightly shorter than that of its orbital period, it would be roughly the same constant face, but over time the moon would rotate relative to the Earth. Again, this is really difficult to describe without a whiteboard, and so you could imagine that over time we'd see slightly different faces. We'd just say see this face for maybe 10 years, and then it would slightly change for the next 10 years in this kind of continuous process. So this would not be truly tidally locked. So in kind of true tidal locking, those periods are the same and this wouldn't happen. But as kind of tidal locking is kind of the end point of the system. It's a dynamically favored system because as for the accretion disk, it's kind of a minimum energy solution for this tidal locking. But over the course of getting there, the moon wasn't created like this. So at one point, the moon would probably have rotated a lot faster than it orbits the Earth, and we'd have been able to see all the sides of the moon. And over time, through tidal interactions, so the same forces that cause the tides to go up and down on Earth, would have caused the rock to move and deform on the moon, and this gets rid of energy. And so over time, these two periods, the rotational and the orbital period of the moon, become matched up. And so just before tidal locking, it would have been semi-tidally locked, which I guess you could think of as kind of precession. But yeah, hopefully that answers your question. Yeah, without whiteboards, some of these things are really difficult to kind of describe in kind of this space that I've got.
When we get back to Cambridge, I'll bring you a whiteboard and then.
Perfect. Thank you very much.
Okay.
So yeah, it's 8 o'clock or 7 o'clock UK time. I think we've actually managed to get through all the questions this week, which is really good. Thanks. There's some really thought-provoking questions there as well. I'm gonna have to go in and think about some of those. So we'll be back next week. Kind of get your questions in on Slido, or there's a form on the Cambridge Astronomy website. Please do tune in again and put questions in the chat for then if you can. But yeah, so we'll see you all next week. Bye.
Bye.